Hello, everyone, and welcome. I'm excited to have you here today. We're going to be exploring the Wastewater Laboratory Safety and Testing Guide. This is a comprehensive resource designed specifically for laboratory professionals working in wastewater treatment facilities. Over the course of this presentation, we'll cover essential safety protocols, analytical methods, and quality control procedures to help you work safely and effectively. So, let's get started and dive into this important subject together. Let's talk about some fundamental laboratory safety rules that are crucial for everyone's well-being. First, food and beverage prohibition. It's really important that you never eat, drink, or apply makeup in the lab. Pathogens like hepatitis, typhus, giardia, cryptosporidium, and toxic chemicals can easily contaminate food and drinks, which could lead to serious illness or even be fatal. On the flip side, bringing food or drinks into the lab can also contaminate our samples, causing inaccuracies in tests like BOD, TSS, and phosphorus. So, keeping food and beverages out of the lab is essential for safety and data integrity. Next, let's look at storage protocols. Always remember that food and drinks should never be stored in the same refrigerators or areas where samples are kept or tested. Keeping these separate helps us prevent cross-contamination, which is vital not only for your safety, but also to ensure our test results remain reliable. Finally, a quick note on acid handling. When working with acids, always pour acid into water, never the other way around. This might sound simple, but it's a critical safety rule. Do this in a fume hood or a well-ventilated area. Think of the phrase, "Do what you otter." Add acid to water. Pouring water into acid can cause violent, exothermic reactions and dangerous splashes, so always remember to add acid to water carefully and cautiously. These safety fundamentals are the backbone of a safe and effective laboratory environment, and they connect directly to our overall goal of conducting accurate tests while protecting everyone here. Let's talk about the importance of material safety data sheets, or MSDS. These documents are essential because they provide critical safety information for handling hazardous substances. For instance, they include physical data such as melting points, boiling points, and flash points, which help us understand how the material behaves under different conditions. MSDS also outline toxicity levels and potential health effects, so we're aware of the risks involved. They detail first aid procedures, which are crucial in case of accidental exposure. Additionally, they specify reactivity and storage requirements to ensure safe handling and storage practices. Disposal procedures are also covered, guiding us on how to dispose of chemicals responsibly. Protective equipment specifications are included to make sure we're properly protected during handling. The MSDS describes spill and leak procedures, enabling quick and effective responses to accidents. Now, an important aspect we need to remember is regulatory compliance. Wastewater treatment plants must keep MSDS for all chemicals they use. This is not just a good practice. It's a requirement under the Federal Hazard Communications Standard, 29 CFR 1910.12. Having these MSDS on hand becomes especially critical during spills or emergencies, as they provide emergency personnel with the necessary response procedures. So, essentially, MSDS are vital tools that help us protect ourselves, our colleagues, and the environment, while also ensuring we stay compliant with regulations. Let's talk about equipment ventilation and chemical storage, which are crucial for safety and sample integrity. First, proper venting of muffle furnaces and drying ovens is essential. This helps prevent safety hazards and avoids contaminating samples. When you dry samples, volatile substances can be released that might be hazardous to health. Forced air ovens can also aerosolize bacteria and viruses, putting workers at risk of exposure. Additionally, moisture from drying can create corrosive environments that may cause instruments to fail prematurely. And if you're drying wastewater samples, venting ammonia into the air can contaminate your samples and blanks, which affects your results. Now, moving on to chemical storage best practices. Always store chemicals in cool, dry places out of direct sunlight, preferably in cabinets designed for that purpose. Keep liquid chemicals below eye level to avoid splashes or spills. Remember to date chemicals when you receive them and record expiration dates. This helps ensure you're working with safe, effective reagents. Store acids separately from other chemicals and below eye level for safety. Always check the labels for hazard information before handling any chemicals. Keep MSDS sheets accessible so you can review safety information when needed. Never store chemicals in unmarked containers. Label everything clearly. And if you prepare reagents in separate containers, make sure those are labeled properly as well. All these practices are about protecting yourself, your colleagues, and maintaining the quality of your work. Proper ventilation and chemical storage are integral parts of a safe, efficient laboratory environment, fitting into the bigger picture of good laboratory practices. When it comes to collecting samples, there are a couple of main methods we use. The first is the grab sample. This type of sample captures a single moment in time, so it's very useful for understanding conditions at that exact point. However, because it only reflects one instant, it can fluctuate quite a lot, especially compared to composite samples. That's why we usually reserve grab samples for situations where the sample needs to be analyzed quickly, or when the parameters change rapidly over time, like measuring slug loading, or when sample holding times are limited. On the other hand, we have flow proportional composite samples. These are collected over a longer period, which means they tend to give a more representative picture of the water quality on average. This is particularly important when waste characteristics are changing throughout the day or week. For most wastewater treatment plants, flow proportional composite sampling is the standard approach because it accounts for variations in flow and load. The exception to this is pond effluent, where the detention time is so long that fluctuations don't significantly impact the overall loading measurements. Understanding these differences helps us choose the right sampling method to accurately assess water quality, which is crucial for effective treatment and compliance. Let's talk about the guidelines for representative sample collection. The WPDES permit clearly specifies where to collect samples, what types to use, how often to sample, and which parameters need testing. Proper sample collection is absolutely critical because it ensures the results are accurate and reliable. First, let's discuss location selection. When collecting grab samples, it's important to choose spots where the waste stream is well mixed. Ideally, you want to locate the inlet tubes of the composite sampler in the center of the waste stream, away from the sides of the channel, and also off the floor of the flume or channel. This helps ensure the sample truly represents the flow. Next, channel maintenance plays a vital role. Keep the flow channels near metering or measuring devices very clean. Debris, grit, or buildup can cause false readings because they affect channel depth, detention time, or flow rate. Additionally, grease, scum, and debris can interfere with pressure or ultrasonic measurement devices, leading to inaccurate data. Regular cleaning is key. Finally, selecting the right sample type depends on what you're testing. Grab samples are great for capturing instantaneous values and identifying extreme conditions, things like pH, chlorine residual, dissolved oxygen, and fecal coliform bacteria. However, for parameters like BOD, suspended solids, phosphorus, and ammonia, flow proportional compositing provides the most representative data. It's also what's required by Wisconsin DNR for these tests. By following these guidelines, we help ensure our sampling is accurate, representative, and compliant with permit requirements, which is essential for effective water quality management. Flow proportional composite sampling involves collecting samples in proportion to the flow rate of the wastewater. This means that the sampler pulls aliquots directly related to how much water is flowing through the system. For example, the plant's flow meters send electronic pulses, like 1 pulse per 1,000 gallons, that tell the sampler when to collect a specific amount. So, if it's programmed to take 100 milliliters every 10 pulses, it will do so each time 10,000 gallons pass through. This method ensures our samples accurately reflect the flow conditions. Now, when we're testing for multiple constituents, say metals, phosphorus, or suspended solids, each may require different preservatives. That's where subsampling, or splitting, comes into play. Most auto samplers gather wastewater into a single 2 to 3 gallon jug, but for different tests, we need to split this into separate containers. The key here is thorough mixing before splitting to make sure each subsample is identical, which is crucial for reliable results. Speaking of subsamples, they serve several important purposes. First, they help us assess variability introduced during processing or preservation. Second, they allow us to check the precision of our laboratory analysis by comparing results from two parts of the same sample. And third, during DNR compliance inspections, they help verify that our discharges meet permit requirements. Remember, for these split samples to be valid, they must be prepared and analyzed for the same parameters, using the same methods, to demonstrate reproducibility and accuracy across our testing processes. Let's go through some key points for sample documentation requirements. First, it's important to specify the sample type. This could be flow proportional composite, time proportional composite, or a grab sample. Clearly identifying the sample type helps us understand how the sample was collected. Next, we need to record the sample point, which is the collection location. Accurate location information is essential for tracing and analysis. Each sample must have a unique identification to distinguish it from others, so make sure to assign a unique ID for every sample collected. Timing is also crucial. For grab samples, record the exact time and date of sampling. For composite samples, note the first and last subsample times. This information helps interpret the data correctly. Preservation methods are another key aspect, whether chemicals were added or samples were refrigerated, for example. Proper preservation ensures the integrity of the sample until analysis. The initials of the person collecting the sample should be recorded as well, providing accountability and traceability. Now about defining the sample date. It's based on the majority of the sample collection. For instance, if a composite sampler starts at 7:00 a.m. on July 10th, and the last part is collected at 7:00 a.m. on July 11th, we record July 10th as the sample date because most of the sample, 17 hours, was collected on that day. Finally, I recommend including a description of the sample, such as its color, odor, turbidity, or any unusual observations. Also, ensure that the sample container information is detailed enough to trace back to the sampling details. All this information helps maintain the quality and traceability of your sample documentation. Let's take a look at sample preservation and holding times for different tests. For BOD, the sample needs to be analyzed within 48 hours after compositing, and it must be cooled to 6 degrees Celsius or less, without freezing. For TSS, you have a slightly longer window, 7 days, under the same cooling conditions. When it comes to ammonia, you have 28 days, but here you need to add sulfuric acid to bring the pH below 2 and keep it cold, again without freezing. Total phosphorus is similar. You get 28 days, but again, sulfuric acid is added to lower the pH below 2, and the sample must stay cooled. Now, for fecal coliform, the window is much shorter, just 6 hours. You need to add sodium thiosulfate if the sample is chlorinated, and again, keep it cooled to 6 degrees Celsius or less, without freezing. The most critical point here is that all samples must be refrigerated at temperatures not exceeding 6 degrees Celsius, and absolutely must not be frozen. Proper preservation is essential to ensure the accuracy of your test results and to meet regulatory requirements. Let's take a closer look at laboratory glassware and pipette selection. First, volumetric flasks are essential tools, especially when making standards or calibrations. They provide precise volume measurements, which are crucial for accurate standard preparation. Next, beakers and Erlenmeyer flasks are typically used for digestions. However, they are not suitable for standard preparation or any tasks requiring precise volumetric measurements, because their volume markings are not very accurate. Moving on to graduated cylinders, these are appropriate when working with larger sample volumes, such as 50 ml or more, for tests like BOD and TSS. They offer a good balance of accuracy and ease of use for bigger measurements. When high precision is needed, especially in standard preparation, microbore volumetric pipettes, including mechanical pipettes, are the go-to tools. They ensure the highest level of accuracy. For samples containing particulates, wide-bore pipettes are essential. They help prevent blockages and strain from solid particles, making handling much easier. Finally, Mohr and serological pipettes serve specific purposes. Mohr pipettes are used for color reagent measurements, such as phosphorus analysis, while serological wide-bore pipettes are ideal for low-volume samples like BOD influence, or when preserving samples for phosphorus or ammonia analysis. In summary, choosing the right glassware and pipettes depends on the task. Precision, sample type, and volume all guide your selection to ensure accurate and reliable results. Let's talk about proper pipette technique, focusing on volumetric and serological pipettes. Starting with volumetric pipettes, which are classified as TD or to deliver, and this is sometimes marked as X internationally. The key point here is that these pipettes should never be blown out. They are carefully calibrated to deliver a specific volume, and this calibration accounts for any small amount of liquid that remains in the tip. You might notice a colored square at the top of some pipettes. This indicates the volume they are calibrated to deliver. Remember, the main idea is accuracy, and following the proper technique ensures precise measurements. Now, moving on to serological pipettes. These are a bit more versatile because they can measure various volumes from a single pipette, thanks to gradations marked along the tube. There are two main types to know about. First, the blowout type, which is graduated to include the entire tip. You can identify it by two thin colored or etched rings at the top. The second type is the drain-out. These are graduated so that the liquid stops before the tip, and they are marked with a color-coded rectangle or square at the top, but no rings. Understanding these distinctions is crucial. Using the right pipette and technique ensures accuracy in your experiments and helps maintain consistency. So, always pay attention to the markings and follow proper pipetting procedures. Let's talk about the BOD and TSS pipette requirements. When working with less than 100 milliliters of sample, it's essential to use wide-bore volumetric pipettes. These pipettes have larger openings that make transferring samples with particulates, like raw wastewater, much easier and more reliable. Accuracy is a key consideration here. When pipetting samples that contain visible suspended solids, wide-bore pipettes are generally more accurate. That's because narrow-bore pipettes can get blocked or strained by solid particles, leading to less precise measurements. This is precisely why standard methods specify using wide-bore pipettes for both total suspended solids and BOD determinations. They help ensure the results are accurate and consistent. You might also hear these pipettes called macro-bore or wide-mouth tip pipettes. Just a quick note, if you're using factory-made glassware, it's important not to alter it to create a wide-bore pipette. The integrity of the original design is crucial for maintaining accuracy and compliance. So, in the context of our overall testing procedures, understanding these requirements helps us obtain reliable data, especially when dealing with complex samples that contain solids. It's all about ensuring precision and consistency in our measurements. Now, let's talk about pipette accuracy and some important considerations when working with laboratory equipment. All pipettes come with a specified accuracy, but it's important to remember that the error tends to increase as the pipette volume decreases. For example, a 1 ml Class A volumetric pipette has about a 0.6% error, whereas a 10 ml pipette of the same class has only a 0.2% error. This highlights that using larger volume pipettes generally provides more accurate results. Another key point is that a single larger pipette is usually better than multiple smaller pipettes because errors are additive. So, using a 10 ml pipette once results in just 0.2% error, but doing the same task with 10 1 ml pipettes adds up to about 6% error overall. Plus, using multiple small pipettes repeatedly increases the risk of contamination, which can compromise your samples. Now, moving on to incubators and desiccators. These are essential pieces of lab equipment. An incubator provides a controlled, enclosed environment with a consistent temperature, which is crucial for microbial or chemical analyses that require precise temperature conditions. On the other hand, a desiccator is used to maintain a humidity-free environment. It's especially useful for storing oven-dried samples, glassware, and some chemicals before weighing, to prevent moisture absorption that could skew your results. In wastewater labs, desiccators are also used to cool TSS sample filters after drying. They typically contain a color-indicating desiccant, like silica gel, which changes color as it absorbs moisture, from deep blue to pale pink. It's important to note that once the silica gel turns pink, it needs to be regenerated by heating or replaced to ensure it continues to function properly. And always make sure the desiccator lid is sealed tightly, using silicone grease or a rubber gasket to maintain the dry environment. Let's take a closer look at laboratory balances, starting with the analytical balance. This is the most sensitive type of balance you'll find in a lab, capable of measuring mass with an incredible sensitivity of 0.1 milligrams. It can handle weights from just 0.1 mg up to 150 grams, making it ideal for very precise measurements, like testing suspended solids or TSS. Because of its high sensitivity, it's crucial to verify its accuracy monthly, using one weight in the gram range, around 1 to 2 grams, and another in the milligram range, about 100 mg. This ensures ongoing precision. Now, moving on to the top-loading balance. This is more of a general-purpose instrument, usually measuring objects around 150 to 300 grams. While it's less precise, meaning it has lower readability and accuracy compared to the analytical balance, it offers the advantage of quick measurements. This makes it very convenient for tasks where extreme precision isn't necessary, like weighing chemicals when preparing reagents. It's also more economical and easier to use for routine tasks. Just like with the analytical balance, it's recommended to verify its accuracy monthly, using weights within its typical use range. Both balances are essential tools in the lab, each suited to different types of measurements. But the key is understanding their capabilities and maintenance to ensure reliable results. Let's talk about balancing operation and maintenance. First, warm-up requirements are crucial for electronic balances. They need adequate warm-up time to prevent electronic drift, which can cause measurement errors. Always follow the manufacturer's instructions, or better yet, leave the balance on all the time if possible. Remember, cold components tend to drift as they warm up, impacting accuracy. Next, environmental controls play a big role. The balance should be placed on a sturdy, vibration-free foundation. Even leaning on the balance table can affect your results by several milligrams. It's also important to maintain a controlled environment. Consistent temperature and humidity are vital because large fluctuations can damage sensitive parts and electronics. Keep the balance away from direct sunlight and HVAC vents to avoid drafts and temperature swings. Now, onto proper leveling and cleanliness. A level balance is essential for accurate measurements. Use the bullseye level to make sure the bubble is inside the target circle. Keeping the pan and the surrounding area clean is equally important. Use a camel hair brush for dust and dirt, and if needed, clean with mild detergent, lab reagent water, and lint-free wipes. A clean, level balance ensures reliable results. Moving on to measurement protocols. Always ensure your samples are at room temperature. Warm samples can create air currents that disturb the pan. Never weigh chemicals directly on the pan. Instead, use weigh boats or glassine paper to prevent contamination and damage. Also, close the sliding doors during weighing to shield the balance from drafts, which can cause fluctuations. Finally, professional maintenance is key. Have your balance serviced annually by a qualified technician. Over time, weights can get scratched, worn, or corroded, which affects their certified value. Regular professional checks keep your balance in top condition and ensure ongoing accuracy. By following these key points, you'll maintain your balances properly, ensuring precise and reliable measurements in your work. Let's talk about certified weights and drying ovens, which are crucial for maintaining accuracy in our measurements. First, with weights, especially ASTM type 1 weights, it's important to store them in their original case when not in use. This helps prevent contamination and keeps them in good condition. When handling weights, always use plastic-tipped forceps to avoid surface damage from metal-to-metal contact. For heavier weights over 100 grams, wearing soft cotton gloves is recommended, because handling with bare hands can transfer skin oils and acids that damage the weights and alter their mass. It's equally important never to stack weights or let them touch each other, as this can cause scratches or other damage. When cleaning, just lightly dust them with a soft camel hair brush, no harsh chemicals or abrasive cleaning. To ensure ongoing accuracy, weights should be recertified by an external metrology firm at least every 5 years. Also, remember that Type 1 weights, made from high-grade stainless steel, are certified traceable to NIST standards. On the other hand, Type 2 brass weights should not be used for analytical balance verification because they can tarnish and develop pitting, which affects their reliability. Now, turning to drying ovens, maintaining a consistent temperature is key. Several factors can influence this, such as frequently opening and closing the door, overloading the oven with too many samples, or any defects like a poor door seal. The oven's thermostat quality also plays a role, and placement under HVAC vents can cause fluctuations in temperature. To get an accurate reading of the oven's temperature, place the thermometer bulb in a jar filled with clean sand or vermiculite. This insulates the thermometer from rapid temperature changes when opening the door and provides a stable internal temperature reading. Traceable thermometers like this are widely available commercially. By paying attention to these details, we ensure our equipment remains precise, supporting the overall integrity of our measurement processes. Let's talk about reagent water quality, starting with its definition and classification. Reagent water is essentially water that's been specially treated to remove impurities that could interfere with sample analysis. You might also hear it called laboratory reagent water, laboratory pure water, distilled water, or deionized water. The key point here is that this water must meet strict standards, which are typically classified as ASTM type I or type II. Now, moving on to proper storage. It's important to store reagent water only in materials that prevent contamination. For example, Teflon and glass are suitable for BOD analysis, while polyethylene, polycarbonate, and polypropylene can be used for other types of analysis. Remember, once you open a container of reagent water, you should avoid storing it for long periods, as contamination can occur over time. If the water looks cloudy or if its quality has changed, it's best to discard it. Next, let's discuss conductivity evaluation. Conductivity is a measure of how well water can conduct electrical current, and it serves as a good indicator of water quality. Pure water is actually a poor conductor because it has very few ions. However, the presence of ionic impurities makes water conduct better because these ions separate in solution, allowing current to pass through. So, if we measure conductivity and find it's higher than expected, that indicates ions are present, and the water isn't as pure as it should be. Specifically, for ASTM classifications, Type I water should have a maximum conductivity of 0.056 microsiemens per centimeter at 25 degrees Celsius, while Type II can go up to 1 microsiemens per centimeter at the same temperature. These standards help us ensure the water we use maintains the purity required for precise laboratory work. Let's take a closer look at some common sources of reagent water contamination. First, high conductivity is a key indicator. When conductivity levels are elevated, it means there are more dissolved ions present in the water. These ions can come from substances like copper, chromium, or ammonia, which can interfere with our testing processes. For example, elevated trace metals can skew BOD results, while increased ammonia levels can affect ammonia-specific tests. Additionally, when municipal water facilities add phosphates to remove iron and manganese, this can interfere with total phosphorus measurements unless the water is properly treated beforehand. Moving on to heavy metals, copper and chromium are particularly concerning because they are toxic to biological organisms. High levels of these metals can significantly impact biological tests, such as BOD and fecal coliform counts, by inhibiting microbial growth, which can lead to inaccurate assessments of water quality. Next, dissolved organics pose another challenge. These are substances like volatile organic compounds or trihalomethanes, which often originate from chlorination. Carbon filtration is effective at removing many of these dissolved organics, but if the carbon filter isn't functioning properly, these contaminants can pass through. This includes microbial byproducts, endotoxins, and cell fragments, which not only act as toxins themselves, but can also interfere with BOD testing. Finally, it's important to understand the limitations of conductivity measurements. Conductivity only measures substances that ionize in water. For instance, a small amount of sugar, say 1,000 parts per billion, won't affect the conductivity enough to meet type I criteria. Also, accurately measuring conductivity at very low levels, like those required for type I or II standards, is extremely challenging without a closed system and highly sensitive equipment. Plus, atmospheric CO2 can cause ionization reactions that artificially increase conductivity readings beyond the standards for type II. So, understanding these sources and limitations helps us better control and interpret water quality tests. Let's talk about standard preparation and calibration. First, what exactly is a standard? Well, a standard is a solution with a known and documented concentration of the target analyte, like a 100 ppm phosphorus solution. These standards are essential because they serve as reference materials. By comparing the instrument's response to the standards, we can determine the concentration of the analyte in unknown samples. It's important that standards are prepared in solutions similar to the samples we're testing to get accurate results. Now, moving on to proper calibration standard preparation. The quality of your calibration curve heavily depends on many factors. The first and most important is using a very accurate measuring device, either a volumetric pipette or a mechanical pipette, for making your standards. If your pipettes are inaccurate, that inaccuracy will show up in your calibration curve. A main caution here is how you handle the standards before measurement. Any small error in handling or measuring will carry through and affect the entire calibration curve, so precision is key. Calibration standards are typically made by diluting a stock analyte solution in volumetric flasks. This process needs to be done carefully to ensure correct concentrations. Finally, let's discuss reading the meniscus correctly. When you're measuring water or any liquid in a small diameter tube, like a pipette or burette, the liquid forms a concave curve called the meniscus. The liquid touches the container walls and rises slightly, leaving a low point in the center. The correct measurement point is always at the low point of this curve. Remember, always read the meniscus at eye level. If you don't, your readings can be off, which affects the accuracy of your measurements and, ultimately, your calibration curve. Let's start with the fundamentals of biochemical oxygen demand, or BOD. Essentially, BOD measures how much oxygen bacteria consume when they break down organic matter in a water sample. This is a crucial indicator of water quality and pollution levels, especially regarding biodegradable organic material. We rely on BOD measurements in water quality management, ecological assessments, and environmental science to help us understand how healthy or polluted a water body is. Moving on to what makes up the BOD test itself. The test essentially looks at how waste or water impacts the oxygen levels in the receiving system. Bacteria, or bugs, as they are often called, decompose waste, and this process requires oxygen. For the test to be accurate, we need a few key components: a food source for the bacteria, an adequate bug population, a sufficient supply of oxygen, and an environment that's hospitable for these microorganisms to thrive. Now, let's talk about how the test is actually performed. It involves creating a series of dilutions with nutrient-rich, buffered water. Sometimes, we add microorganisms to ensure consistent results. We measure the initial dissolved oxygen in the sample, then incubate it at around 20 degrees Celsius for 5 days. After incubation, we measure the dissolved oxygen again. The difference between these two measurements tells us how much oxygen the bacteria consumed during that period, which is what we call the BOD. Finally, there's the concept of carbonaceous BOD, or CBOD. This is a specific part of the total BOD that focuses only on oxygen demand from carbon sources. The total BOD includes oxygen consumption from both carbon and nitrogen sources. To measure CBOD accurately, we add a pyridine-based inhibiting agent before incubation. This agent prevents bacteria like Nitrosomonas from converting ammonia into nitrite during the nitrification process, allowing us to isolate the oxygen demand attributable solely to carbon decomposition. Understanding these aspects helps us interpret water quality data more precisely and supports our efforts in protecting aquatic environments.